Yeah, but that was still like then the one's gone. That's what it is.
Oh, oh. Okay. Good morning, everybody. So we're gonna get started in a minute. Okay, two minutes from the hours. Guess. Okay, so how are you guys doing with homework? Yeah, I saw that everybody in the class took the prerequisite quiz, which is good. But I did see a lot of you took a couple of times to get 100%. That's great. But I did see a few people get like 20, 60, 65, 40. A few students, not many, probably didn't even try. But if you are the one who's making 40 or 20 out of 100, you should really take your time to go back to your 210 and study for it. Yes, go ahead.
This stuff's about the prerequisites. When are the answers for homework 1 gonna be posted?
Usually it's posted after the due date.
Okay.
Yeah. So if it's not posted, should be soon. Yeah. Yeah. Okay. Yeah. And how was you guys are now familiar with Spice, P-Spice or IoT Spice? Yeah. So because some of the contents were not covered in the class yet for the project, so the best way for you not to forget what you learned in Spice is probably go on, just build some simple models, try to remember what was covered. Now, of course, the material is posted, the YouTube was posted, and there's Mr. Elias Wooden has also posted his lecture notes, and also I posted a very comprehensive LT spice simulation guide in the slides folder. So a lot of information that you can learn. Let me see if we got. I look like we don't get that many students here today. Let's see what happened. Do you have people online? Yeah, we have a few people online. Okay. For those people online, can you hear me? Can somebody say yes? Yeah, okay, good. Thank you. Okay, so we're gonna get started today to continue on the op-amps. We're not gonna spend too much time on op-amps because you guys learned something a little bit in 210. This kind of serves as a little bit of review and of course a little bit deeper, have a more complex circuit. But again, that complexity really relies on your understanding of circuit theory, like nodal analysis and Ohm's law and so on. To really do well in op-amp, because we don't plan to cover the imperfection of op-amps, we also don't plan to cover the non-linearity or non-ideal op-amps in this class. If you want to really master this chapter, which is what in exam number one, on September 30th, it takes about a little bit more than half of the grades for middle term one. You really have just remember a few things, a few properties that we talked about last time. If you look at and we talk about how many terminals you need, like negative power supply, positive supply, and there's of course a ground. So you kind of needing 5 or 6 terminals for op-amp. But most importantly, what we talk about for this ideal op-amp is that the gain is approaching infinity. So that's what we always assume. It is fairly true in most cases of op-amps, because most of the op-amps that you can get, like even you can buy today on DGK, it's about 5,000 to 8,000. So it's really big. It's not infinity, but it's fairly big, right? So that assumption is fairly true. But when we use a feedback, of course, we know the gain typically is about in the tens, probably most of them in the tens. So comparing a 10 to 8,000, that's like less than 1% of error. So it's typically we assume it's that. And from this point, then we concluded that V plus and V minus. My hand cannot be on the screen, so that's why. Is always no, not zero. So V plus and V minus is always the same. This is a kind of derived from the infinity gain, because if V plus and V minus are not the same, even though there's a little bit of difference, multiplied by an infinity gain, it gets some sort of very big output, right? So that's why this two inputs has to be the same in order to get a stable output in a feedback control. So that's a second property. And then the third property is the I plus and I minus, the current that going in to the op-amp is always zero. So let's say this is V minus, V plus. Like VCC, like okay, this ground. So these are the really just these 3 things that you remember. Then you will be able to solve any op-amp problem fairly easily, because you have to apply these 3 principles to any problem. Yes. Very good question. Very good observation. We always do this because most of the time we use negative feedback, and the feedback drawing from up to the back is look easier and look nicer. So it just fits the eye. Yeah, and nothing wrong if you draw the inverting terminal at the bottom, nothing wrong with it. But your feedback line will be on the bottom, not instead of on the top, right? So that's why. Good observation, actually. Okay, any questions about these three properties of op amps? So if not, then you guys remember we have this a couple things that we did was like, for example, we did this one. Now, this again, I just want to use this as example, and then we will move on. So if we have Vi and Vo over here, and this R1, this R2, how do we solve for Vo? Well, because V plus, in this case, V plus is 0, right? It's grounded. So from this property on the left hand, you can see that V minus is equal to V plus, that's 0. So which means we mark down over on the circuit, that's 0 volts. That's 0 volt. And so if that's 0 volts, we can easily calculate current. So R1, let's call it I1. So I1 will be Vi minus 0 divided by R1. And that current, we apply the second property, the current is 0. On the left hand, you see, the current going into the terminal is 0, right? So therefore, we can say I2 is equal to I1. And then now we know that the V minus is 0 minus VO divided by R2 equal to I2, right? So from here, we can see that minus VO equal to R2 times I2, and then minus like V minus 0, right? So VO equal to minus R2 over R1 times VI. So we got this output is actually negative, but it's a proportional to R2 over R1. So that's a very typical what we call inverting amplifier. Why? Because input is positive, output is negative, so it's inverted. The sign is inverted, so that's what we call it inverting. Now we also talk about the non-inverting input, so we're not going to repeat it here because we talked about it already. Now we're going to use another example. Look at this addition circuit. You know, in digital circuit, you probably know a lot about additions, but here we want to add all the input to the output. Now this circuit is fairly simple. Now you guys remember, we need to do what? Node analysis, and also, of course, the property of op amp. Now remember, this I minus is 0, and this V plus is also 0 that was given. So V minus is 0. That's marked on the circuit. So V minus 0. And therefore, if you look at the nodal right here, that's a super node. That's a super node. Sorry. You see that super node? You get a current, a couple of currents coming in, then you got one current coming out. So you probably can conclude right away without even thinking that the current I on top that goes through RF is going to be the summation of I1, I2, I3, 9, right? You guys get it? Yeah, okay. So we can write down that the current I, what happened to my pen? Let's see. What's going on here? Look like it's computer's frozen. It doesn't respond to any key. What I'm gonna do? Okay, we might have to do something. I'm sorry about this, but it's really not my fault. But something's wrong. Well, I'm not even able to. I guess I can do this. Actually, okay, let's see. What about that? Oh, okay. It's coming back. Okay. Oh, okay. Good. Some reason it did. Okay, I'm sorry, but okay. So we minus 0, and we know the super node, so we can write down that something happened. I lost my writing capability. Let me redo this. Let me redo this. This is troublesome. Okay. I think that the program stopped. This stopped somehow. I don't know why. Let's see. Okay, yeah. Maybe well, I don't even have a. Do we have any pens I can write? Okay, let's continue. I guess this device is just dead. It won't even switch to. It doesn't switch to DocCam or anything else. Just it won't turn off either. This is terrible. Where's the phone that I can call? Just to have a phone call. Just.
Hello, case of this, how may I help you?
Yeah, hi. I'm in classroom HH214. The screen is not responding.
Help this, you have to
Oh, okay. Okay, got you. Thank you. Hi, I'm HH214, and the classroom desktop computer is stopped responding, and also the control module is not responding to anything. HH214. Yeah, the pin is lost connection, and also the control module can switch between Mac, PC, and .com. It doesn't respond. Oh, okay, thank you. HH, yeah, Happy Hall 214. It says microphone something. Okay, now actually it looks like it did come back. Let me before you go, let me try. Okay, before you go, let's see. Actually, it's been holding on here for a couple of minutes, and look like. Let me see if I can write on it. Okay, yes, I can. How do I change the color to red? The pen color, the pen, the smart pen.
Hello?
Yeah, hi. How do I change the smart pen color?
So it's either on the screen or the monitor itself has different pen colors. Or if not, while you write, there should be like a pen icon
Oh, okay.
that appears on the screen.
Yeah.
If you click on that, it will give you a variety.
Well, it doesn't give me any color. It just give me one color. Okay, now I got it. Thank you. Yeah. All right, but I apologize for that. But okay, so let's get it going. So if we go back to this slide, we can write I equal to I1 plus I2 plus IN, right? And then we know that I1 is equal to V1 minus 0, which at the minus terminal divided by R1, and I2 equal to V2 minus 0 divided by R2, and then you have da 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 da. So now you add all these i's together, then you plug in this I into the equation over here, you get the total I. And now we know that the voltage across RF is going to be 0 minus VO divided by RF equal to I. So therefore, we know that VO equal to minus I times RF. Now, if you plug in all this I in there, you get minus RF over R1 plus RF over R2 plus da 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 plus RF over Rn times, oh, sorry, there's a V1, there's a V2, there's a Vn. Okay, so as you can see, this is called summation or addition because we are adding the voltage of our V1, V2, and Vn all the way to get VO. But of course, each one has a different resistance ratio. Yes, go ahead. Oh, really? Oh, okay. Okay. Well, that bottom equation is already printed over there. Yeah, so you can, I mean, you don't have the copy, it's right over there. So what we're doing addition. So with this op-amp properties, we can do a lot of stuff. Like, for example, in this case, you already know that we can have, like, what we call this one, V3, V4, let's call it V01 here on the top. So from the previous screen, you know that V01 already equal to R A over R1 times V1 plus RA over R2 over V2, and then we add a minus sign. Oh, okay, we add a minus sign here. So now you know that VO equal to minus RC over RB times VO1 plus RC over R3 times VO1, and then plus RC over R4. This is VO1, this is V3, and V4. So minus sign here. So then you plug V1, VO1 to here, you'll get the expression of VO. So apparently, V1 and V2 are added with the ratio, but VO is a summation of V1, V3, and V4, but VO1 is negative, right? Because VO1 is negative. So now actually you are subtracting our V3 and with summation of V3 and V4, and then actually minus the absolute value of VO1. So that's how you can get even multi-stage working here. Okay, why I want to move this thing? Okay. So I'm probably not going to do too much examples. I want to dive into a non-inverting. So you can see from this circuit, you probably already see the difference between what we did before. In the inverting amplifier, we added voltage across at the non-inverting terminal, but now we actually moved the voltage to the positive terminal. Now you might question, oh, is that still positive feedback or negative feedback? Well, it doesn't matter where you apply the voltage, which terminal. The feedback is looking at where the output is connected. If you look at the output, it's connected back through R2 to the negative terminal, which means this is a negative feedback. So for negative feedback, it's always stable. So we can see that now we know V plus equal to Vi equal to whatever value. Let's say 2 volts. Let's say this is 2 volt. So you guys tell me, what is V minus at this point? How much is V minus? 2 volts, right? So given our previous example, it's going to be 2 volts. And then how much is current? Now I'm going to mark the current this way, okay? So just for easier to calculate, you can draw that way too, but you will get a negative sign. So what is I1? Can you guys do it together? So the V minus 0, right? Divided by R1, which is going to be equal to Vi, so it's going to be Vi divided by R1. Let's say this is 10K, and this is 20K. I'm just giving you some example. So Vi is 2 volts divided by 10K, so you get 0.2 milliamps. Okay, so now I'm going to ask you, what is I2? Let's mark it on there. How much is I2? I2 equal to I1, okay? And then how much is VO now? Can you say VO equal to I2 times R2, and then I2 is 0.2, so this is 0.2 times 20K, so 0.2 times 20K, 0.2 times 20, milli, this K, milli and K cancel, you get what? 40 volts? 4 volts.
Why R2 is VO?
I'm just asking you guys, is this correct or not? Doing what? Yeah? Can you use it in series? What do you think? Yes? Why? Yeah, because you are right. You can use it because the current over here is 0. The current into there is 0. The two is in series. My question for you guys is that, can you get VO equal to R2, I2 times R2? Is that correct? Oh,
no,
no? Why?
because the direction of current is going away from
That's not the right explanation.
that direction going the opposite direction.
Yeah,
So
yeah.
it would be negative.
No, 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 no. No, that's not wrong. Yes, go ahead. No, you can I1, I2 is equal. You can add them. They're in the same, like because the current into the negative terminal is 0, so I1, I2 are the same. Okay, what is that? What's there? Add the voltage R1. Why? Okay, so actually the reason is, so this is wrong, okay? So the reason is VO minus, you get VO minus V minus equal to I2 times R2, which means VO equal to V minus plus I2 times R2, which is equal to, and right down here. So VO is actually VI plus I2 times R2, because VI is here is like 2 volts plus I2 is 0.2 times 20. So that gives you 4. So that gives you 6 volts. And VO, see here, VO is positive. And VO is actually more than VI because this here is just, if you write down, it's actually 1 plus R2 over R1 times VI equal to VO. The final equation is VO equal to 1 plus R2 divided by R1 times VI. So VI is the input. And because output is positive, so we call this a non-inverting input, non-inverting amplifier. Yeah.
Like, you see this more regularly in a circuit or the other one?
No, both. Both, yeah. Both. Yeah. All right. So yeah, I guess initially I didn't hear what you said exactly. You say I1 plus I2. I got it. I didn't get that. Okay, so so this is how again, you know, finally I just give you this equation over here, and the steps was find this diagram gives you exact steps like number 1, number 2, number 3, number 4, number 5, and number 6. Get the answer. So it's fairly simple to go through that process. All right. Now we have another interesting circuit. And this circuit, we have input at the positive terminal, and then we have output connected right back with the negative terminal. And there's no resistance at all in the circuit. So in this case, what you already saw the name of a unit buffer. So that's an interesting setup. So because we have V plus equal to VI, that's what's given. And we know that VI equal to V plus, so that must be equal to VI. Now your VO is connected where? Directly with the line, no resistance. But even if we put a resistance, nothing would change because there's no current, right? So basically, the voltage at V minus and VO is going to be the same, and therefore it's going to be VI. So finally, your conclusion is VO equal to VI. That's called unit output. So it is a unit output, and then you get a name called unit buffer. It's a buffer, like buffer means it's not directly connect your input to another device. It's through this op-amp. And one of the questions initially student would ask right away is that, why would you do that? If you get an input and equal to output, why don't you just simply connect it? Well, remember the other two properties that we didn't use today is the input output resistance of op-amp. How much is input resistance of op-amp? Infinity. And what is the output of the output resistance of op-amp? 0. So what it means that this is the equivalent circuit, which means you get the input coming in, regardless of how much resistance of your internal source. 100% is applied as input. And for the output, and then you get the one input 1 times, so the voltage is the same unit again. And your output is 100% of your voltage source, regardless of how much load resistance you have. So we can do a quick example on this one. I don't know if you guys can see from the back, but if you add a voltage source as an input with a resistance of, let's say, 100K, and we're going to add a load resistance of, let's say, 10K. So I want you guys to find out how much current is going through, let's say this is, I just for simplicity, I got 10 volts over there. And so apparently your VO is going to be 10 volts, right? So how much is IO? And VO over 10K is going to be 1 milliamps. So this is very simple. You got input, you got output. Whatever input now is applied to the output. Now, if I'm going to do another circuit, it's like direct connection. So what I'm doing is I connect my source with this internal impedance directly with the load resistance without amplifying. How much current would you get for IO? So give me 10 volts divided by 100K plus 10K. It's going to be like 110, like 0.1. Oops. 0.1 milliamps. It's going to be 0.1 milliamps, which means if I have this op-amp, I got my output resistance 10 times bigger than if I don't have an op-amp. So this is like no op-amp, simply low input impedance plus, and then you get output load resistance, right? So this is why the unit buffer is a very important thing to use. Now, in the future, you guys see that the unit buffer might have a resistance at the feedback, but it doesn't change anything because there's no current. If there's no current, which means we might still same as VO. Okay. Now, why do you have a resistance, or why do you don't have a not having a resistance? Well, because the resistance actually changes the feedback impedance, which might help you with in the future frequency response, bandwidth, things like that. But here we don't have to dive into that. Yeah. Go ahead.
I kind of missed. What, could you clarify again? What's the benefit? It's like we have a bigger current, or well, wouldn't it be that you're getting a constant current regardless of what our RL is?
Well, RL changed, the output current would change. Yeah. But what you get is you get a bigger current. That's what you want. Because, for example, if you want to drive your speaker and you want to amplify, let's say, a boom, 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 you want to amplify it, right? So if you don't have an op-amp, you only get 0.1 milliamps, which is not loud enough. But now with the op-amp, you almost get 10 times louder. Okay, the current is bigger, the output power is bigger. No, it's not a current amplifier. It's not called a current. I'm just using current as an example. Okay, so now we can dive into another example. Here, we get input of V1 and V2. So when you guys looking at this, you might have already wonder, okay, now we know here, this V plus and V minus got to be the same, okay? That's no question, always do that. But the problem is that, what is over here? Now you got V1 here and V2 here. Should be this V1 or should be that V2? Or should be something else? This is something, why not V1 and V2?
The voltage at that point needs to only be one value.
Okay, yeah, that's good. That's a really good explanation. Yeah, and plus, we know that another important property is that the current going in this branch, 0. If this is 0, basically what happened to these two resistance? They're in series, right? So what you need to do is you need to do kind of loop analysis to find the voltage over here. Because let me write that. So very interesting phenomena. If you have trouble to get like how to do this, you can add like the complete drawing here. So assume this is V plus. What you can do is you can say V1 minus V plus over 1K. That's the current going through that top 1K should be equal to V plus minus V2 divided by 3K. That's the current to this branch. See, the current going through 1K, it has to come out. And then the current over here is 0. Now from this equation, you can multiply 3 both sides, and then you can get 3V1 minus 3V plus equal to V plus minus V2. And then we move on this side to 4V plus equal to 3V1 plus V2. And we got V plus equal to 3V1 plus V2 divided by 4. So really we got the V plus. Now once you have V plus, you know that what is V minus? V minus is going to be same as V plus, whatever that value is going to be. And what is VO? What you can do still, use VO minus V minus. That's the voltage. It's going to be, let's call this current I3. It's going to be I3 times that 7K. So from here, you got VO is going to be I3 times 7K plus V minus. Now, what is I3? What is I3? Well, I3 is going to be, I'm going to write on the top. I3 over here, because the current here is 0, so I3 is going to be here as I don't want to call this I4. So it's going to be same as I4. And what's the I4? So I4 is going to be that V minus 0 divided by the top 1K resistance. Yeah, you guys get it? So the I3 is going this way, but because V plus is found, so V minus is going to be same as V plus, and V minus divided by 1K gives you a current of I4, and I3, I4 the same. So VO minus V minus it gives you 7K times that I4. So these are simple nodal analysis by using the property of op-amps. So we're not going to spend too much on this. Okay, now only one step further is I want to find what is the current of IL and what is the current of IO. That's kind of important because, so in this case, we have Vi equal to 1 volt. So therefore, V1 equal to Vi equal to 1 volt. V1 is over here. And therefore, I1 equal to V1 divided by 1K equal to 1 milliamps. And I2 equal to I1 equal to 1 milliamps, right? And then VO equal to, or if you still don't get it, you can get it. So V1 plus I2 times 9K. V1 is 1 volt plus I2 is 1 milli times 9K. So 10 volts. So VO is 10 volts, and we can find IL is going to be VO over 1K. The final 1K is going to be 10 milliamps. So now you guys tell me what is IO? Well, you see I2 and IL both coming out of the node. So therefore, it's going to be I2 plus IL. It's going to be like 11 milliamps. So by this point, you know that the load current is actually provided by the op-amp. And even the current I2 is actually also provided by the op-amp. So IO is output current of the op-amp. So why is this amplifier? What is amplifying? In the early example, we get more power. Where is it coming from? It's coming from the op-amp. So op-amp can supply current, it can also sink current. It can also absorb current. So IO, in this case, coming out, but in some other applications, actually going in. So going in means sinking, so current is going in there. If coming out, it calls supplying current or sourcing current. So, so this op-amp actually supply current. Where is the power coming from for the op-amp? Well, from power supply. We don't enjoy it. We don't enjoy it here because it's ideal op-amp. But the positive and negative power supply gives you the power that you need to amplify the input to get a higher output. Okay. So we're going to move on. Probably. Okay. So we're going to move on to talk about the a difference amplifier. A difference amplifier usually takes sometimes called differential amplifier. So really, it takes the difference of two inputs. That's called a differential amplifier. In the future, you see quite a bit of this circuit. So this circuit has two terminals over there. That's the input. I mean, that's the input to something else. But you have kind of three voltage sources. And this one is called common mode input, and then the other called differential mode input. So, and then you might say, okay, what exactly does it mean? Now you guys still remember superposition, right? So, so in any circuit, linear circuit, we can always do superposition. So when you do superposition, what happens to the voltage sources? If you do one voltage source, what happens to the other sources? Huh? You short them, okay? For current source, you open them, right? So for voltage source, you short them. So in this case, exactly, if you have a circuit, what you want to do is you want to do one by one, so do superposition. That's the easiest way to do. So if we do superposition, then I can show you how it looks like. Let's say there's op-amp. Let's say there's op-amp. And we got, oops, anybody can teach me how to erase? Yeah, I really don't know how to erase things. Okay, well, just do it this way. So let's forget about this. Let's say we got this input coming in. This is op-amp, okay? Now this is not grounded. Forget about that, okay? If we apply this input over here, I'm going to do this. Just make it bigger. So this is the input. This is the input. 3 voltage source input and connect to the op-amp negative and the positive terminal. Now, it probably get quite confusing. Okay, the 3 voltage sources. Well, now what do I do, right? So, in fact, actually, they might not work. So I might need to have some sort of resistance in each branch. Okay, so called R1, R2, and RF. Because there are 3 voltage sources, so it would be very difficult to start with. You can always do nodal analysis. I mean, there's nothing wrong to do that. But for simplicity, what I'm going to do is I'm going to do superposition for all 3 voltage sources. Okay. So for VICM, when I do VICM, what happens to VID divided by 2 and then the bottom and the top 2 things? They become short circuit. So which means, so I'm going to do it here. So for VICM, so I'm going to have input right? Because I shorted the top one, I shorted this one, I shorted this one. So that's my input. Now, by looking at this input, what do you think? The voltage at the positive and the negative terminal, how much is it?
Well, the voltages at the positive and negative terminal always have to equal each other.
Yeah, they have to equal each other, right? You're right. So basically, the voltage source coming in, and So there's no current going into this branch. So therefore, the voltage here is going to be the same as voltage here. And the voltage same over here, and the voltage here same over here. So which means for the negative terminal, they get the same input. So we call it common mode. So the positive and negative terminal have the same input. It's called the common mode. Okay. So now let's do the differential. Let's do differential means we're going to short the common mode voltage, which means this one here. We're going to short it, not open it. We're going to short it. So the circuit becomes so actually this circuit may not be correct in the future. Maybe not, because if the voltage here is 0, 0, 0, yeah, right. So you guys, you know what? I'm gonna get this to 0. I'm gonna short it because otherwise we might have trouble. So we might actually just open this. Okay. Let me do this. Okay. You know what? I'm gonna add another slide here. I'm going to go back just one more slide. So basically, what I'm going to do is I'm just repeating because that one is actually may not be correct. I'm going to just do another example here without feedback, because with that feedback, the current might mess up. Actually, may not be working at all. So when we have the common mode, which means so we have V plus equal to V minus equal to V ICM. So that's what we have for the common mode input. And then for the differential mode input, we're going to short the common voltage, the common source, right? So when we short it, you see in the middle, we short it. So now you actually get the voltage at the top and the bottom. Each one is 1/2 of the differences. So that's why it's called a differential input. So we can go through some interesting examples here to make it easier, because other feedback didn't really work very well. So in this case, we have two input. Now, remember you guys had earlier we talked about the additions, right? So with the additions, we add all the input. Now, when we add them, what we did is we connect them all to the same input terminal. Now we are connecting the V1 and V2 to the two different terminals. We're going to actually find out the output is the difference between the two inputs with some ratios. So the way to do this to start is that here, and you guys know that the voltage across into the positive and negative terminal is always 0. That's good. So now I'm going to look at V plus. So guys, looking at R2 and R1, R3 and R4, looking at R3 and R4, what can you say about the connection? Are they in series, parallel, or whatever, nothing, or something else? They're in series. They're in series. The reason is there's no current into the positive terminal. So basically, what you're looking at is just this, right? So this is R3, R4, this is VI2. So, and then if they're in series, we can find out what is V plus. V plus is going to be voltage divider. It's going to be VI2 over R3 plus R4 times R4, right? You guys get it? Because of water divider. Okay, so now we know that V minus is going to be same as V plus, right? That's another property of op-amp. So now okay, so we're not going to, well, we can write down to Vi2 over R3 plus R4 times R4, right? So that's V minus. Okay, so now we find V minus. We want to find the current I1 and current I2. So what is the current of I1? Now remember, no current going to the negative terminal, which means the current through R1 has to be V minus minus VI1 divided by R1. Now VI1 we already find it. V minus we already found it. We already found it. So it's going to be R4 over R3 plus R4 times Vi2, and then minus Vi1, and then divide by R1. So we get I1. So now you guys know that I2 is going to be same as I1 because there's no current again going to the negative terminal. So what is VO? Well, we know that VO minus V minus divided by R2 equal to I2. Or in other words, VO equal to I2 R2 plus V minus. So now you can plug in this one to here and this to here. You can get VO. Now, VO minus VO, yeah. So I didn't have the chance to derive the actual expression, but when you plug in everything in, basically you can see here, there's a minus sign. So if you, for example, we take a certain ratio of R4 was R2 and minus VI1, right? So you plug all that in, you got here. Now when you plug in that one into here, you multiply R2, right? So, and then you have that V minus also plug in here. You can do some mathematics. But ultimately, what I want to tell you is that the output is the difference between Vi1 and Vi2. Now, of course, there are some ratios before them, but you can always make the ratio in the final expression. You can make the ratios like equal to each other, which is possible. So this is called a difference amplifier. So what we're doing is we amplify the difference between V1 and V2. Okay, the application of this is a lot of applications. If you have two different inputs, they cannot use the same ground, so therefore you take the difference. Like for example, in your iPhone, you got multiple batteries in series, like 2 or 3 of them in series. So when they're in series, when you want to match the voltage of one cell, you cannot do it. There's no ground because let's say if you start from 0 here, and this will be like 3.5, and this will be 7.2, right? So for the bottom one, yes, there's a ground here. You can take the output, go to op-amp, you can do it. But for the top one, there's no ground. You cannot do it. So therefore, you have to use a difference amplifier. So that one just look like the circuit. Like if you want to do op-amp, okay, you want to do another op-amp, okay, down here, like you do another op-amp. So each one of them is going to be a difference amplifier. So we take the difference here, but of course the bottom one has a ground, which you can use a regular amplifier. But for this one, we take the difference between here and here. For the top one, we take difference between here and here. So that's called difference amplifier. It's very useful circuit. Let's go on. Yeah, so we talk about superpositions and so on. So we do that. Common mode gain. Yeah, we already talked about the common mode gain. So for the common mode, that's why in the initial drawing, I had to remove all the stuff with that. See here, you have a common mode input going to the same negative and positive terminal, of course, through some resistances. If we want to find the output Well, the question is that, is there any output, right? So if the circuit is ideal, there's no output because the common mode, there's no output. But if the circuit is imperfect, you always have some output. So in this case, we can find out basically you can still do 0 amps here and 0 amps here. So remember, those current coming into the terminals are 0, right? So therefore, and also, so this is slightly different. So when we have this like a differential amplifier or difference amplifiers, I mean, in the future, like when you guys take into 430, you know that there's always some difference at the input that you actually amplify the differences. It's not like the ideal op-amp we talked so far is that, okay, the negative positive terminal are always the same. So it's slightly different. So in this case, what we are doing is we're still using ideal op-amp, which means we will still say that I plus, V plus, and V minus are going to be the same. So if they are the same, if you look at it here, same means this is like a short circuit. If that is a short circuit, what you're doing is you're doing this voltage source yeah, so it's R1, R2, and R4, R3 here, R3, R4. So this is VICM. Because there's no current going into the each terminal and the two voltages are the same, so we basically try to connect them into like together. And therefore, you have this one here, R2 and R3 are in parallel. So basically, you got this V plus and V minus equal to VICM times R4 over R2 in parallel with R3 plus R4. Oh, R1. Yeah, R1, R3, I1. I1, sorry. Yeah, it's R1, that's right. It's equal to VICM, R1. No, R4. It is R4.
R2 is the one that.
R4, R1 and R3, yeah. R1 and R3. I hate this writing. It doesn't work. How can I do it better? So, well, here. So eventually, what they're doing is here, give this equation, and R3 and R4, R3 and R4 times VICM instead of what I wrote here. So forget about here, right? The problem is doing here, we have a problem because even though the voltage are the same, here, but the current here is 0. But the current here is not 0. So sometimes we just have to be really careful. We said the voltage are the same. We always say that. But we cannot simply make them short. Yes, go ahead.
Right, through R3 is necessarily 0. We'll have some current going through R3 and then through R4. Right?
Yeah. The current going through R3 and R4 is actually, and you're right, not necessarily 0, right? Because the current going into the terminal is 0, but this two current may not be 0. And if this current not 0 and the current in R1 also may not be 0. So therefore, the two currents are not the same, right? So we have a little bit trouble of getting like exactly how much. But one thing for sure is that we have voltage source here, which going up there, and also this voltage source over here. So this R3 and R4. Because the current here is 0, but R3 and R4 is in parallel, so we can say that V plus is going to be V ICM divided by R3 plus R4 comma R4. So from here, so this is wrong, okay? So now we got V minus, so now V plus is equal to V plus. And therefore we get I1. Now we can have I1 equal to V ICM minus V minus divided by R1. So, and then I2 equal to I1. And finally we have V minus minus VO divided by R2 equal to I2. So these are the correct equations to find out. Now, if you plug in all these equations, you will definitely find that the output, how much is the output with regard to input. So that's for the common mode input. And then, so this is the differential amplifier. When we look at the input resistance, we actually now are doing a virtual short circuit. So because these two virtually is the same, so we are doing this R1 in parallel with R1, the two in parallel, and then R2 at the bottom. So, okay. So this circuit is actually quite simple because R1 is the same. So we have basically going through this, this current are going to be the same. And this current going here is going to be the same. So because this two becomes a watch point, so V plus and V minus is going to be the same. But it's not 0 in this case. It's not 0. So we can say that, and also notice that VID, the bottom is positive instead of up is positive, right? So we can do VID. So VID going this way. So this is what we get for the input, and if we do this R1, because this is virtual ground, so therefore the current going this way, I mean supposedly going that way, but we know that the current actually doesn't go into the terminals, but actually current coming from R2, it's current coming from here and go this way, and the other current going this way, it's coming this way. So if we do this current IID, so IID equal to VID over R1 plus R1. So therefore, you can say your input resistance is VID over IID equal to R1 plus R2. So that's how you can really just find the resistance by using that virtual short circuit. So it's quite useful to do the input resistance. And of course, if we get to even more complex circuit, the first thing I want to tell you is don't get scared. Okay, a lot of students, probably because of lack of preparation from previous, let's say, node analysis experience, and get like anxious. Why? Oh my gosh, the circuit is so big. Actually, there's nothing to worry. You just have to remember a couple of things. The positive and negative terminal, the voltage always the same. There's always no current going into each of the positive and negative terminal. Like those two things, if you remember, it's always help you to do any circuit regardless the complexity of the circuit. Now, in this case, this is a difference amplifier. It takes input of VI1 and VI2. It's through two different amplifiers. And of course, this is the second stage of S3. Now, in this case, we think that A1, A2, S3 are infinity, okay? It's just very big. Even though it's written A1, A2, S3, but we think it's very big. The reason they write A1, A2, S3 because in the future, we talk about imperfect op-amps, they start to kick in, okay, A1, A2, S3, see what happens. But in this particular example, or in this chapter, we don't do that. So we think they're still very big. So when we have the circuit, we always start looking at the properties of op-amp, whether it's input current no zero or whether it's voltage same as positive negative input terminal. So we can look at one by one. So guys, look at the top, look at the A1, So VI1 is connected to the plus sign. So which means the O here is VI1. By applying the property of op-amp, the negative terminal for A1 voltage should be VI1. So exactly, so that's easy to get one. So which means the voltage over here is going to be VI1, okay, VI1. So we got that voltage. Can we find, they call this VO1. Can we find VO1 yet? Probably not, because we need to know the current over here, but we don't know the current, right? So we cannot find the current, the voltage. However, so now let's move on to the bottom op-amp. So look at the bottom op-amp. VI2 is connected to the positive terminal of A2. By employing the property of A2, what is the voltage at the negative terminal of A2? It's VI2, right? So now we find the voltage of VI2, and we find voltage of VI1. So clearly, we can start looking and find the current. Now let's call this current I1. So writing together, how much is I1 is going to be? It's going to be VI1 minus VI2 over R1 plus R1. Okay, so this is a little bit confusing because you might say, well, there's a ground. So these two are not actually in series. Now, however, in this particular example, the ground actually is added. It's in the actual instrumentation, there's actually no ground here. Okay, they add this for simplicity, for symmetry. Because if you look at the circuit, it's actually symmetrical. So there's no current going here anyway. So okay, so we can remove that ground for this example. If we remove ground, so it will be even better. So now you find I1. Okay, now you find I1. So what is I2 then? What is I3? So basically, this is equal to I2 and equal to I3, right? Because there's no current. The current over here, 0. The current here is 0. So now we can easily write, okay, so what is I2? Is VO1 minus VI1 divided by R2 gives you I2. And VI2 minus VO2, this is called VO2 at the bottom, divided by R2 gives you I3. But I2, I3 are already found. So therefore, you can easily find VO1 and VO2. Now, I'm not going to write it, okay? So just you guys can manipulate the equation and find I1, VO1, and VO2. So which means we have VO1 here and VO2 here. And we go to the second stage. Well, the second stage is same, this 0 amp into the terminal, and we call V plus, V3 plus, and V3 minus. So from the bottom circuit over here, we know that V3 plus is going to be VO2 times R4 over R3 plus R4. So what is divider, guys? Look at here. So this is the VO2. There's no current here. So these two are in series. Therefore, the voltage divided. So this voltage is VO2 divided by R3 plus R4 times R4. That's the voltage. So once we find this voltage, V3 minus is given, because V3 minus and V4 minus are the same. So this is going to be same as V3 minus. Now, so V3 minus, so therefore we have V3 minus VO1 divided by R3 equal to VO minus V3 minus divided by R4. So that's another equation. So from this equation, you can find VO, which is going to be some number. And this equation here, again, I'm not going to, it's actually already derived here. So VO1 is actually here, and VO2 is given over there. You see the symmetry, R2 and RY. If these numbers are given, then you can get this. For example, if these two are the same, you got 1 plus 1 is 2. So VO1 and VO2 both amplify, right? And then from here, you got this equation, and you can manipulate to find VO. So this is a very useful instrumentation circuit, okay? So we're going to stop here, and Thursday, we're going to go over some integrators and differentiators, and we're going to jump into the next chapter, okay? Remember to submit your homework on time, okay? Then you get the points almost free. Yes. Let me.
So VO2 shouldn't be VO2 minus.
Give me 1 second. Let's see.
I know.